In Chapter 5, we're going to talk about stoichiometry, which is chemical math. In order to understand chemical math, though, we have to be able to talk about how we envision chemical changes or chemical reactions occurring, and that is evidenced by the chemical equation. So let's talk about chemical reactions. The difference between a physical change and a chemical change is quite large. A physical change alters the physical state of a substance without changing its composition. So a physical change would be something like water boiling or water freezing. It's changing state, but at its heart, steam and ice are still water. The underlying material hasn't changed. Now, that's different than a chemical change. A chemical change is going to actually change the composition. So what we have here is hydrogen peroxide, which is given by the formula H2O2. And when you pour it on a cut, it bubbles. Those bubbles are oxygen gas being given off. So oxygen gas is being given off, and water molecules are actually being formed as well. So it's no longer hydrogen peroxide, it's something completely different. So a chemical change converts one substance into another. And this happens through not either, you kind of have to have both. You have to break bonds in the reactants, which are your starting materials, and you have to form new bonds in the products. Okay? So, for example, the H2O2, if I were to draw the Lewis structure for this, it would look like this. When I turn that into water and oxygen gas, we know what water looks like. That's HOH, like that. And O2 has a Lewis structure that looks like that. So we can see we've had to break some bonds and make some bonds. Okay? So break new bonds, or break bonds in the reactants, form new bonds in the products. Here's another reaction. The reaction of methane and oxygen to go to carbon dioxide and water. This is probably best illustrated that I've got carbon with hydrogen attached to it. In the products, carbon is attached to oxygen, so we've definitely had to break the CH bonds. The oxygen was bonded to itself, so we had to break oxygen-to-oxygen bonds. In the products, we've got two different types of bonds we're making. We're making H to O bonds and carbon to O bonds. So, bonds broken, bonds formed. So how do we show a chemical reaction? We do that through writing chemical equations. Okay? A chemical equation shows us what's happening to the materials by showing us the formulas for both the products and the reactants. Okay? And the way we do this is pretty standard. Reactants are written on the left. Products are written on the right. Now, we use coefficients in front of our formulas to count out the number of molecules or atoms present. This has to happen because of the law of conservation of matter. Matter is neither created nor destroyed in a chemical reaction, which means that if I take methane and react it with oxygen, the number of carbon atoms has to be the same in the beginning as it is in the end. The number of hydrogen atoms needs to be the same as in the beginning and the end, and the number of oxygen atoms needs to be the same in the beginning and the end. So you can see here, CH4 plus 2O2 goes to CO2 plus 2H2O. I've got one carbon and one carbon. I've got 4 hydrogen, and I've got 2 times 2. That's a total of 4 hydrogen. I've got 4, the 2 times the 2, oxygens. And over here I've got 2 oxygens, and then I've got the 2 times the 1, so 2 plus 2 is 4 oxygens. So this is a balanced chemical equation. And this is just restating what I just said. The law of conservation of mass, or matter, states that atoms cannot be created or destroyed in a chemical reaction. We use coefficients to balance the equation. And a balanced equation is going to have the same number of atoms of each element on both sides of the equation. So here we have a color-coordinated accounting of our atoms. Now there are some other symbols that you need to know used in chemical equations. First one being the reaction arrow. The reaction arrow tells us that the reaction is occurring, something's happening. Okay, you have to have a reaction arrow, otherwise it's not a reaction. There's also the delta here, which tells us that we're heating something up. Okay, now this can be used in a couple of different ways. We can use it both as a reaction or a product. We'll talk about that when we talk about energy. Or we can put it above the arrow to say, hey, we're cooking something. Okay? Now, we also throw in our states of matter. So we use S for a solid, L for a liquid, G for a gas, and AQ for an aqueous solution. This means dissolved in water. So whatever state your atoms or molecules are in is shown in the chemical equation. So let's balance a chemical equation. So the example here is write a balanced chemical equation for the reaction of propane, C3H8, with oxygen to form carbon dioxide and water. So reactants go on the left side, products go on the right. So we're reacting propane with oxygen. So C3H8 plus O2. Then we use our arrow to say that the reaction is occurring. And we're making, how do I know? Because it says to form carbon dioxide and water, so CO2 and H2O. We never, ever, 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 ever change the subscripts to balance an equation, because if you change the subscripts, you're no longer talking about the same material. So we can only place coefficients in front of these molecules. So, what I do is I balance elements one at a time. So, really the first thing I do is count the number of atoms on each side. So, I write it down the center, C, H, and O. I see that there are 3 C's on that side, 8 H's, and 2 O's. On the product side, before we put that 3 there, I'd see that there's 1 C, 3 O's, don't forget because I've got 2 there and 1 there, and then 2 hydrogens. Now, the key here is I want these numbers to be the same on both sides. Okay? So the first thing that I'm going to do is I'm going to use the carbon. I'm going to balance the carbons first. And that's why they placed a 3 as a coefficient. Now, when I do that, I take the 3 times the C. That means I've got 3 C's. But now, I also go back and recheck everything. How many oxygens do I have now? Well, I just added a 3 in front. This is saying that I've got 3 CO2s now. 1, 2, 3 CO2s. That means I got 2, 4, 6, plus 1, 7 oxygens left. Okay? So whatever you multiply in front gets multiplied throughout the whole compound. 3 C's, 3 times 2 oxygens gives us 6, plus the 1 over on the water, that's our 7. Now, we're going to balance hydrogens next. Okay? So I've got 8 hydrogens on the reactant side and 2 on the product side. So I'm going to put a 4 in front of the water. That now makes that 4 times 2 is 8. So let's check my carbon, hydrogen, oxygen. That gives me 8. That was 2, 3, 2, 7. So now that gives me 8 of those guys. And now, how many oxygen do I have? I've got 3 times the 2 is 6. Plus 4, that gives me 10 oxygen. So the next step is to finally balance the O's. And if I place a 5 in front of the O2, that gives me 10 oxygens on each side. The next thing we do is we make sure that it's the smallest set of whole numbers. Okay? If they're divisible by any number, and equally divisible by any number, then we don't we always go to the smallest set of whole numbers, okay? So let's say I'm balancing the equation and I came up with 2, 10, 6, 8. Well, all of those are divisible by 2. So divide everything by 2. 2 divided by 2 is 1. 10 divided by 2 would give me 5. 6 divided by 2 gives me 3. 8 divided by 2 gives me 4. Okay? So, balancing chemical equations is actually pretty simple. It's all about everything. The hard part comes is if you have an incorrect reactant or product formula. If you have the wrong reactants or wrong product formulas, this can be very, very difficult, if not impossible. Okay? Now, the book just says do the carbon first, the hydrogen, then the oxygen. There are some good rules of thumb to follow. Number 1, don't start with hydrogen or oxygen. Try to leave to the end. Okay? The reason is with hydrogen or oxygen, they often show up in multiple places. Okay? Number 2, don't start with anything in more than one reactant or product. Okay? Because if you try to start with those, whenever you change something, any number, you're going to change those all the time. So we try to leave those to the end. Okay? Those are the 2 best rules of thumb that I can give you. So, sometimes there's some tricks you can play. Okay? C8H 18 plus O2 goes to CO2 plus H2O. Let's do this one as an example. Carbon, hydrogen, oxygen. I've got 8 carbons on the reactant side, 1 on the product side. 18 reactants, 2 on the product for the hydrogen. We've got 2 on the product side and 2 on the reactant side, 3 on the product side for the oxygens. So, notice oxygen is in a reactant and 2 products. Leave it to the end. Okay? The one thing that we can start with is carbon. So, if I put an 8 in front of the CO2, now that gives me 8 carbon, but now I'm at 2 times 8 is 16 plus 1 is 17 oxygens. So then I'm going to balance out my hydrogens. I've got 18, so what times 2 is equal to 18? So I put a 9 in front of my hydrogen. Now, let's go back and check and see how many oxygen does that give us. That's 8 times 2 is 16 plus 9. That's 16 plus 9 is 25. So I need to multiply something times 2 to get 25. What times 2 equals 25? Well, not a whole number. If I use 12, that's 24. If I use 13, that's 26. So what I do, and this is a trick you can use only with our diatomic elements. Okay, remember diatomics? Hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. What I can do is, what times 2 gives me 25? Well, the answer is 12.5, or 25 over 2. That now gives me 25 oxygens. But we don't leave it like that. Whenever you see that you can use this little half trick, you have to then multiply everything by 2. So this becomes 2C8H18 plus 25O2 goes to 16 CO2s plus 18 H2Os. Okay? You can only use this with the diatomics. Remember? Hydrogen, oxygen, nitrogen, fluorine, chlorine, bromine, or iodine. All right, let's talk about the mole and Avogadro's number. We already kind of touched on that in the lab this past week. A mole is simply a unit of measurement of counting, and it contains 6.02 times 10 to the 23rd stuff, items, okay? Like a dozen. If I've got a dozen eggs, it's 12 eggs. If I've got a dozen chickens, it's 12 chickens. If I've got a dozen donuts, it's 12 donuts. If I have 1 mole of chickens, that's 6.02 times 10 to the 23rd chickens. If I've got 1 mole of eggs, that's 6.02 times 10 to the 23rd eggs. So you can see that it's the same as a dozen. It really is. It's not numerically the same, but the concept is the same. So, 1 mole of carbon atoms is 6.02 times 10 to the 23rd carbon atoms. 1 mole of carbon dioxide molecules is 6.02 times 10 to the 23rd CO2 molecules. 1 mole of water molecules is 6.02 times 10 to the 23rd water molecules. This 6.02 times 10 to the 23rd is what we call Avogadro's number, and I often write that as capital N sub capital A. Okay? Avogadro's number. Now, Avogadro's number is a really big number because atoms are so tiny. We need a lot of them to group them so that we can count them by weighing them. So we can use Avogadro's number as a conversion factor. Okay? And we use moles, atoms, moles, molecules. Okay? The fun thing is Avogadro's number, 6.02 times 10 to the 23rd, actually only has the unit of inverse moles, or per mole. That means you could put whatever you want on the top. You could put chickens per mole, molecules per mole, atoms per mole, eggs per mole. Okay? We're obviously going to be using atoms and molecules most often here. So, this is a conversion factor. 1 mole is 6.02 times 10 to the 23rd atoms, or 6.02 times 10 to the 23rd atoms is 1 mole. Similarly with molecules. 1 mole of molecules is Avogadro's number of molecules, or Avogadro's number of molecules is 1 mole of molecules. So how many molecules are contained in 5.0 moles of CO2? Okay? So, whenever we have word problems, what I like to do is I like to pull out the information that I'm given and the information that I'm looking for. So I'm given 5.0 moles of CO2. And I want to know, what is the number of molecules of CO2? It's a question mark. So now, I'm looking for a number of molecules. That means I'm going to use Avogadro's number as a conversion factor. But how do I use that conversion factor? Well, if I take a look at the conversion factors, I can have moles on the top, molecules on the bottom, or molecules on the top, moles on the bottom. Let me use this one to cancel out the moles. So 5.0 moles times Avogadro's number over 1 mole. The moles cancel out, and that gives me 3.0 times 10 to the 24th molecules of CO2. This is why if you're still struggling with dimensional analysis, it's a really important thing that you go back and continue to work on that. And reach out. Let me know if you're still struggling a little bit with dimensional analysis. If you're still having problems, please tell me. So as I said, we use Avogadro's number to count atoms by weighing them. So really, how does this work? Well, there are several things that are at play here, okay? To break it down into its simplest bits, I'm going to talk about 3 things that are numerically the same but have different units, okay? So you find these things exactly the same way, but they're going to have different units, okay? The first one is the formula weight. This is the sum of all the atomic weights of all the atoms in a compound. Technically, this is for ionic compounds. And it has the units of atomic mass units. So, for example, FeSO4, iron 2 sulfate. This contains 1 iron atom, 1 sulfur, and 4 oxygen atoms. So what I'm going to do is I'm going to look at the periodic table and determine what is the mass of iron, what is the mass of sulfur, and what is the mass of oxygen. I've got 1 iron, 1 sulfur, and 4 oxygen. I'm going to add all those masses. So 1 iron atom is 55.85 AMUs. 1 sulfur atom is 32.07 AMUs. 4 oxygen atoms at 16 AMUs each, so 4 times the 16. When I add these guys up, I get 151.92 AMUs. Okay? These atomic mass units are for really tiny things. They're for the single pieces of these compounds. Okay? Just 1 iron, 1 sulfur, 4 oxygens. Okay? That's the smallest indivisible pieces. So similar to the formula weight, we have the molecular weight or mass. And this is the sum of all the masses of elements present in a molecular compound. Okay, so molecules. So what I'm talking about is things like H2O. I got 1 hydrogen and 1.01 AMUs, or 2 of those guys, sorry, and 1 oxygen at 16.00 AMUs. So that's 2.02 and 16.00. So the molecular weight or molecular mass is 18.02 AMUs for water. Okay? Notice it's the same thing as the formula weight. It's just one's for molecules, one's for ionic compounds. Now the third one is the molar mass. Okay? The molar mass is the mass of 1 mole of any substance reported in grams. Technically what I say is it's in grams per mole. Okay? So this is going to give us the same thing as our formula mass or our molecular mass. The only difference is the units is in grams per mole. And this works because we have agreed that carbon is our set point. Okay? And the set point is 1 mole, which is Avogadro's number, of isotopically pure carbon-12 has a mass of exactly 12.00 grams. Okay, so isotopically pure carbon-12. Carbon comes in 3 different isotopes: carbon-12, carbon-13, carbon-14. So if I make pure carbon-12, okay, 6 protons, 6 neutrons, 1 mole, Avogadro's number, 6.02 times 10 to the 23rd, carbon atoms will weigh exactly 12 grams. Okay? So what this means is all of these mass numbers on your periodic table, the weight was given in AMUs, the molar mass is now given in grams per mole. 12.01 grams per mole. So the molar mass relates the number of moles to the number of grams. That means molar mass is a conversion factor. Anytime you see something over something else, it's a conversion factor. Grams per mole, miles per hour, days per week, seconds per minute. Those are all conversion factors because they're relating one substance, one quantity of a substance to another quantity. So let's talk about how we do this. How many moles are present in 100 grams of aspirin? And they tell us aspirin has the formula C9H8O4, and they tell us the molar mass is 180.2 grams per mole, which is great. They already tell us what that is. So, I'm going to take a look at my original quantity. That's that 100 grams of aspirin. And we want to know how many moles of aspirin is this. So, I'm going to write 2 different conversion factors where I've got grams of aspirin per mole, or 1 mole is grams of aspirin. I'm going to choose this one because I want to get rid of grams of aspirin. That's my unwanted unit. Unwanted units go in the denominator. So now I take the 100 grams of aspirin times 1 mole divided by 182 grams of aspirin. That gives me 0.555 moles of aspirin. Okay? A couple of things to watch out for. Always write your units. Units need to be on here. But the second thing is, write what you're working with. We need to keep track of the number, the unit, and now we need to keep track of what the substance is. Because you're going to see we can relate number of particles of one substance to number of particles of a different substance using a chemical reaction. Now we can also use this to determine the number of molecules in an atom. Not number of molecules in an atom. Number of molecules in a mass of a molecule or atoms. Okay? So since that's 180.2 grams of aspirin is 1 mole, that means 1 mole is 6.02 times 10 to the 23rd molecules, or we've got a new conversion factor here of 180.2 grams of aspirin over 6.02 times 10 to the 23rd molecules. These are exactly the same, but it depends on what you're given, what is it you're trying to get rid of, what is it you're trying to find. So here we have another problem using aspirin. How many molecules are in a 325 milligram tablet of aspirin? Again, they give us the molar mass. So the original quantity we're given is the 325 milligrams of aspirin, and we want to find the number of molecules of aspirin. So the first thing we need to do is write out our conversion factors. Now, molar mass is in grams, not milligrams. So what I want to do is I would convert milligrams to grams. So 1,000 milligrams is 1 gram, or 1 gram is 1,000 milligrams. Since I want to cancel out milligrams, that needs to be on the bottom. So this is the conversion factor I'm going to use. Then the other conversion factors, grams of aspirin per molecule or molecules per grams of aspirin. I'm going to use this one because I want to find molecules. This needs to be in the numerator, because that's what I'm looking for, is the number of molecules. So I set this up, 325 milligrams of aspirin times 1 gram over 1,000 milligrams, that cancels out our milligrams, times the number of molecules in 1 mole of aspirin, 180.2 grams of aspirin. That cancels out our grams. And we get 1.09 times 10 to the 21st molecules. Now, you can do it this way. And this is perfectly acceptable to use those conversion factors as is. But another way that I like to show the relationship between moles and mass and all that good stuff is through the use of islands. So I've got what I call particle island. I've got another island that I call mass island. And I've got a third island here, which I'm going to call mole island. Now, to go from particle island to mole island, I got to cross a bridge. To do so, I divide the number of particles by Avogadro's number. To go from moles back to particle island, I have to do the reverse, so I would multiply by Avogadro's number. To go from mass island to mole island, I would divide by the molar mass. MM is molar mass. To go from mole island back to mass island, I would multiply by molar mass. Okay? So in that previous example, when we were given the 325 milligrams of aspirin, I still need to convert that to grams, so 1 gram is 1,000 milligrams. What I would do, following this little pattern, is I would multiply by the molar mass. Divide by the molar mass. the other side. Divide by the molar mass. So 1 mole is the 180.2 grams of aspirin. And then to go from mole island to particle island, I use Avogadro's number. I would multiply by Avogadro's number, 6.02 times 10 to the 23rd molecules of aspirin for every 1 mole of aspirin. And I would get the exact same number, okay? Because it's exactly the same thing mathematically. I just like this better. I think it's a neat little diagram that you can use to help understand how to move back and forth between these islands. Now, the fun part is that those islands are not alone, okay? A balanced chemical equation tells us the number of moles of reactants that combine to form the number of moles of products. So if I have N2 plus O2 making 2NO, 1 mole of N2 and 1 mole of O2 will make 2 moles of NO. Okay? Notice that coefficient 1 has been written for emphasis. It's not supposed to be there. We don't put the number 1 in those as coefficients. Okay? So, not only is it the number of molecules, but it's also the number of moles. So this allows us to make conversion factors from the coefficients, which we call mole ratios. Okay? So if I want to ratio nitrogen to oxygen, I know that 1 mole of N2 reacts with 1 mole of O2. Okay? If I want to ratio N2 to NO, 1 mole of N2 to 2 moles of NO. If I want to ratio O2 to NO, it's 1 mole O2 to 2 moles of NO. Now remember, all of these have an opposite form too. This first one would be the same 1 mole of O2 over 1 mole of N2. Those are exactly the same. 2 moles of NO for every 1 mole of N2. Those are the same. 2 moles of NO over 1 mole O2. Those are the... So I get 6 different conversion factors based on this balanced chemical equation. We use the mole ratio to allow us to go from moles of one thing to moles of a second thing. This mole-to-mole conversion factor. I like to call that my golden bridge. Okay, my golden bridge. Because if I think of moles of A as an island and moles of B as an island, remember I've got my particle island out here. I've got my mass island. So these will be particles of A, mass of A. Over on the other side, I could have particles of B and mass of B island. And my bridges here are the same as they were that we just talked about. So to go from particles to moles, I divide by Avogadro's number. I multiply by Avogadro's number to go the opposite way. To go from mass of A to moles of A, I divide by the molar mass. To go from moles of A to mass of A, I would multiply by the molar mass. My golden bridge here is my mole ratio. And on the other side, guess what? Those bridges are exactly the same as they are on the other side. To go from moles of B to particles of B, I would multiply by Avogadro's number. The reverse would be to divide by Avogadro's number. To go from moles of B to mass of B, I'd multiply by the molar mass. And the reverse would be to divide by the molar mass. So now I've got a complete map that I can use to go from one thing to another thing based on a balanced chemical equation. So here we have a balanced chemical equation. 2C2H6 plus 5O2 goes to CO2 plus 2CO plus 6H2O. We want to find out how many moles of carbon monoxide are produced from 3.5 moles of C2H6. So I've got 3.5 moles here. I want to find moles of CO. So now I need to look at my balanced chemical equation, and I need to relate the the ethane to the carbon monoxide. Anyone notice an issue? This is not balanced. This should be 4 COs. So here, that should be a 4. And now I got my conversion factors. 2 moles of C2H6 over 4 moles of CO, or 4 moles of CO over 2 moles of C2H6. I want to cancel out my ethane. So now, 3.5 moles of C2H6 times 4 moles of CO over 2 moles of C2H6 gives me 7.0 moles of CO. So let's continue with another one. Using the balanced equation, how many grams of ozone, O3, are formed from 9 moles of O2? And here's our balanced chemical equation. This time it is balanced. So I've got moles of reactant, O2. I'm going to find moles of product, and then grams of product. So mole to mole conversion factor, then molar mass conversion factor. This is just like our island. So this is mole A, mole B, mass B. So I use the 2 moles of ozone for every 3 moles of O2, and that's going to cancel out my O2. And then I use the molar mass of ozone, which is 16 grams per mole of oxygen, times 3 of those guys are 48.0 grams per mole. And we know that when we go from moles to mass, we multiply by the molar mass. So 48 grams goes on top. We set up our conversion. We've got our 9 moles of O2 times 2 moles of O3 over 3 moles of O2 times 48, or 290 grams of ozone produced.